Welcome to the third lecture of this course. So, let us recall from the last lecture that given a matrix A over a field, let us say here, as I said, here you can consider a field, by a field here you can consider either it is Q, R or C. So, given any matrix, our aim is to reduce that matrix to a simpler matrix by applying elementary row operations. So, if you remember applying elementary row operations, another name for that is also row reduction. So, given any matrix A, we would like to reduce it to a simpler matrix. And why are we interested in this? Because if we are given a system of linear equations, then we want to reduce the system into a simpler system where we can solve, which we can solve without facing any difficulty. Therefore, we want to treat this, we want to treat the reduction of a matrix in the generality. So, let us also recall that given any matrix, the steps in the reduction, again by reduction I mean row reduction. So, given a matrix, the steps in the row reduction are not unique in the sense that given any stage, there are plenty of choices for the elementary row operations to be applied on. So, if the same matrix is given to 5 different people, each one will apply the elementary row operations according to his or her wish, and that might result in 5 different final matrices. Some of those matrices might be good, some not. So, like we have to this show, this tells us that it is perhaps a reasonable requirement that we have to fix some terminal point. Of course, when a system of equation is given, you consider its augmented matrix, then you can start reducing that, and you can stop at any stage whenever you feel like now you can solve the system, now you can solve the system easily. But when we are treating the issue of reduction in the generality of any given matrix, there we need to fix a terminal point that where as it is not a sensible idea for one to keep on going. So, we need to fix a terminal point, and exactly that is given by row echelon matrices. Okay. We have defined that in the last lecture, and we defined these terms row reduction and row equivalence. So, row reduction, as I said, it is just nothing but applying some elementary row operations, and row equivalence means if one given two matrices, if one can be reduced means, again I said, row reduction, that is applying elementary matrices or elementary row operations. So, given to matrix, if one can be reduced to another, then we say these matrices are equivalent, and this relation is an equivalence relation. So, now in the last lecture we proved that given any matrix, it can be reduced to a row echelon matrix. Okay. Of course, as we have shown that given any matrix, I can reduce it to a row echelon matrix, and that proof we have done by the method of induction. But the following question comes very naturally here. As we have said that we need to fix a terminal point, if given a matrix, if it is equivalent to 2 different row echelon matrices, then again our original our aim to fix a terminal point is now under challenge. Okay. So, we need to show that this cannot happen, that is given a matrix. We have to show that it is equivalent to means in the sense of row equivalence, it is equivalent to one and only one row echelon matrix. So, one part we has done, that is its equivalent to one row echelon matrix. Now, we need to prove that it is the unique. So, before we do that, let me show you something. So, as I said that the main motivation for considering this row echelon form or row reduction is we would like to solve a given system, right, a system of equation. So, we are talking about, given a system of equation, we consider its augmented matrix and then we will reduce it to a stage, and here the stage will be the row echelon matrix, which is equivalent to the given the augmented matrix, which is associated to the given system of equation, right. Now, we just have to see, we just to explore, we just have to confirm that indeed reducing it to a row echelon form, that gives us the solutions of the given system without facing any difficulty. So, that gives the solutions of the system without, I mean, any sort of difficulty, I mean, in the sense that the system is at, I mean, the final after reducing, the system is at such a stage that we can solve them immediately. Okay. So, let us see. So, given a system, let us say Ax equals to b, where A f and b is a row vector, b is am cross 1 f. The augmented matrix associated to that is this. Now, we will reduce it, we are applying row operation. Let us arrive at this. So, let A prime B prime be the row echelon matrix, which is equivalent to this. So, this is so far we do not know that whether applying another operations we can get a different row echelon matrix or not, but what we are just saying that given the system we can arrive at a row echelon matrix which is equivalent to that. Now, as I said, I would like to show that indeed this reducing it to a row echelon matrix is actually quite very helpful to us, in the sense that now we can solve the system immediately. So, how? So, for that let us make some observation that suppose this is our system, this after reduction, suppose this looks like this. So, in the row echelon matrix there could be some rows which are entirely 0. Now, there might be 3 other blocks. So, the reason for writing this in this way will be clear immediately. So, let us first observe that this is a block of size m cross 1. Okay, this is a block of size m plus 1. So, basically this is the last column of this matrix. So, the question is whether this column can have a pivot. I repeat, whether this column can have a pivot. So, suppose this column has a pivot, then it will look like 1 and 0 0 further, right? Because from since the row echelon form, the pivot cannot appear in a row other than this. Now, if you see this, then then what does this say? Suppose it contains a pivot. That means if assume that you have only r number of non-zero rows and rest of the rows are zeros. Well, I mean, you have r number of rows here r number of rows here, and this is one row, and rest of the rows are completely 0. Okay. So, the first we see that possibly first r plus 1 rows are non-zero and rest of them are 0. Then you see what is the r plus 1th equation of this new system. Remember, this system is equivalent to the original system. So, the last equation is, if you denote the variables by x1 up to xn, 0 xn equals to 1, right. This is the r plus 1th equation of the system, and clearly does not have a solution. So, what you get is, suppose after the row reducing it to a row echelon matrix, reducing the given the augmented matrix of the given system to its row echelon to a row echelon matrix, if the last column contains a pivot, then it cannot have a solution. So, that speaking contrapositively, if the situation indeed has a solution, then the last row cannot contain a pivot. Let me write that. The row echelon for the row echelon matrix equivalent to the augmented matrix has a solution, the row echelon matrix equivalent to the augmented matrix has a pivot in the last column, this implies the given system has no solution. If I label this system as star has no solutions. Okay. So, this is the, so that is in order a sufficient a necessary condition for the system star to have a solution is this row echelon matrix equivalent to the augmented matrix indeed cannot have a pivot at the last column. Okay. What about its converse? That is, suppose the last column does not have a pivot, then can we say that it has solutions? Try to understand, we are talking about the converse. Earlier we seen that if the last column has a pivot, then it cannot have any solution. So, that means solution exists, that means last row cannot have a pivot. Now, we are talking about the not last row, last column, the last column cannot have a pivot. Now, we ask the opposite one, suppose the last column of this matrix does not have a pivot, whether one can have a one can show the given system as a solution or not. Let us also see that. So, that is also quite easy to see. Suppose this is as I said that let us assume that J1 up to Jr are the let us assume that for some r, first r rows are non-zero, r rows are non-zero and rest are 0. Okay. So, for this first, so those r rows are now on the top of this matrix and the 0 rows are placed at the bottom, and now our assumption is that the last column does not have a pivot. So, this is the entire block is now 0. Okay. And these are first r rows which are non-zero. Fine. Yeah, possible system has m. So, it's m minus r. Okay. and this does not have a pivot. So assume that as the pivot of the first row lies at the J1 column, the pivot of the second row is at the J2 column, similarly the pivot of the rth row is the rth column. Okay. Once that is there, so thus, well, let me, fine. So the variables corresponding to this columns are xj1, xj2, xjr. Okay. So earlier we had n variables x1 up to xn. So now these n variables are now divided into two classes. In one class you have the variables which correspond to the columns containing pivots, and you have the other variables which are n minus r in number. Remember, n minus r can be 0. For example, if after reducing it to row echelon mat form, it just becomes for example some so let us say some identity matrix and 0 elsewhere, then you see that r becomes equal. So since it is the whole identity matrix, so n minus r is 0 in that case. So n minus r could be 0. So thus I am not saying that always there will be a variable which corresponding to some. Well, again let me repeat, if you are confused what I am saying, that you may not have any variable which is not coming from a column containing no pivots. Okay, you may not have any variable, all your variables might be exhausted. Okay, so suppose that you have some variables which are not coming from the columns containing the pivots. So you will have n minus r such variables. We will simply re-label the variables for the sake of simplicity in notation. So the variables which are other than this, we re-label the rest n minus r variables. I would like to emphasize on the fact that this could be 0. So if there is no variable other than this, then you don't need to do anything. So if there are variables, let us relabel them. So relabel them as u1 into un minus r. Okay. This is one thing we will do, and again for the sake of simplicity in notation, so these variables u1 into un minus r, they are so in the given system of equations, in each of these equations these variables have some coefficients attached to that. So we for the sake of simplicity in notation, we will also relabel those coefficients. So what we do is for I in 1 up to m, in the ith equation, we relabel the coefficients of these variables u1 into un minus r by C11 up to C1 n minus r, sorry Ci1 up to Ci n minus r respectively. Okay. Fine. So after this relabeling, what is now how does the ith equation look like? So after this relabeling, so yeah, so let us because when I is beyond r, then anyway everything is 0, so we can simply ignore them. So thus for any I from 1 up to r, what is the ith row here, or in terms of equation how does the ith equation of this reduced system look like? Okay. So easy to see that the first non-zero entry is in this matrix is 1, because these are the rows which contain pivots. So, the ith equation well, so okay, so I think instead of using I, it would be rather much more convenient if I use rather k, C k1. Okay. So, the kth equation now looks like the following. The first, so before this term, so k, just a minute. So, the kth equation, it first starts with the variable x j k, because kth equation has its pivot as the j kth column. So, x j k, because any term before that, any entry before that is 0, plus you have the terms corresponding to the variables u1 up to un minus r with their appropriate coefficients. And furthermore, since it is a row echelon matrix, in that for that equation there is no other term containing these variables except x j k, right. So, therefore, the kth equation now looks like for the following C. So, it will be j from 1 up to n minus r, C k j x sorry u u j. Okay. That is how the kth equation looks like for any k in 1 up to r. Okay. So, what does that show? For any k I have now such a equation, and for different k these are different. Does not that show the following, that if we assign arbitrary values to these uj's, then from these equations we can immediately determine the values of the variables x j k. So, what I mean is the following, that so assign arbitrary values to the variables to uj's. So, let's say we set uj equal to, let us say something some zj, where zj from f and j from 1 up to n minus r. Okay. So, if we assign arbitrary zj's with the corresponding uj, then it is easy to see that for any k lying from 1 up to r, x kj is nothing but summation n minus r c kj j. Okay. So, thus what is going to be the solution? Because by definition a solution is a pair in Fn. So, what are the entries in the is not by a solution is by definition a tuple, an n tuple. So, if so, what is going to be the coordinate? What is going to be the coordinates in this tuple? So, it is now easy to see from here. If suppose I want to know the kth coordinate. So, if k is from 1 up to, if k is from 1 up to r, yeah, so x kj, how many exactly x. So, therefore, there will be r coordinates here which will come from the equations, and rest of them will be free. So, in this tuple, so general jk coordinate for any k, the jkth coordinate is going to be summation Ckj, Zj, J from up to 1 minus r, and other coordinates, and if I is not equal to jk for any j, then well, if j is not equal to jk for some j, then jth coordinate is basically this zj. Zj. Okay, that is how you get a solution. So, as I said that the way we are finding solutions here is the technique, the method that the technique, the method, the way which we are adopting to arrive at a solution is not at all different from what you have done for when a specific matrix with numerical entries or specific system of equations with concrete numerical entries are given. I mean and you solve it by reducing it to a row echelon matrix. So, the technique, the method that you apply there, general proof also involves the same. Okay. And as I said in the beginning that our aim is to formalize the things, because we have made a lot of computations earlier. Now, I want to formalize the things and to organize the things, so that I can understand what is actually going on, and when further when it is required, whenever it is required, I can use the method in a much more organized way, because I have settled things in the generality. Okay. So, therefore, I am not giving any concrete example now. So, I have just discussed the method in the general setup. So, I would encourage you to take some system of equation and first solve it in your way by reducing it to a row echelon form. Then you see that the way you do it, it is exactly same as this. So, I leave this to you to convince yourself that what you have done earlier and what we have done in the for a general system, they are exactly same. Okay, let us go ahead. So, what we have just shown, we have shown if the last column does not have contain a pivot, then we do have solution. So, thus the converse holds. Okay. So, let me again repeat. So, given a system, we consider its augmented matrix, reduce it to a row echelon form, and that whenever we arrive at the row echelon form, if the last row of the row echelon form, sorry, I mean by row echelon form I means that row echelon matrix which you have arrived at, if that row echelon matrix has one in the last column, has a pivot in the last column, then the row corresponding to the pivot, the equation it gives becomes an inconsistent equation, because in the sense that it does not have a solution. Therefore, the original system cannot have a solution. So, that is the first thing that we have observed. The second thing is, if it does not have any pivot in the last column. So, if it does not have any pivot in the last column, it has to be of this form. Okay. Because if the last row just above this goes completely 0, and here you have something non-zero, so again it has to be pivot. So, therefore, it cannot happen. So, the thing is whenever you have a row, you have a non-zero row here. So, up to what I mean is, up to this point you must have a non-zero row here as well. That is quite easy. That is obvious. So, thus what I mean by that is, the non-zero rows appearing in this block are same as the non-zero rows appearing in the bigger block when you consider add this column 2 and rest 0. So, whenever this is the situation, we have we may have some variables which are not coming from any column containing pivots. So, we relabel, for the sake of simplicity, we relabel the variables and their corresponding coefficients in all the equations. So, therefore, now for any equation, for any row here, the corresponding equation becomes this, and that shows us how to solve. Okay, fine. So now let us go ahead. So throughout you see I kept, I unintentionally kept on telling the row echelon form, the row echelon form. You see every time I am using the word the. So whenever we use the word the, it requires a justification in the sense that we have to establish it is unique. So before getting into this, that how reducing it to row echelon form, we solve a system. Before getting into that, I was talking that we need to establish the uniqueness of the row echelon of the row echelon matrix for a that you have arrived by through reduction from a given matrix. Okay. So I just said that it's unique but didn't prove. So let's now prove. So once you prove that for any given matrix, by reducing it, you can only you arrive at one and only row reduced echelon matrix. So once you have the uniqueness, then it is legitimate to call it the row echelon matrix associate equivalent to the given matrix, or in another word which I am actually unintentionally kept on using is the row echelon form of a given matrix. So I repeat, given a matrix, we need to show that by reducing it, it is equivalent to one and only row echelon matrix. So this row echelon matrix, after proving the uniqueness, will be referred the row echelon as the row echelon form of A. Okay, so now let us get into the proof of uniqueness. Okay, so as I start with a m by n matrix. So we would like to prove by contradiction. So assume that from this A, by applying row reduction or elementary matrices, we can arrive at, by using two different sequence of row operations, elementary row operations, we arrive at two different row echelon matrices. So R1 and R2 are row echelon matrices. Okay. We would like to arrive at a contradiction from if R1 not equal to R2. So how to do that? First observation is that R1 and R2, since they are both equivalent to A, so R1 and R2 they are also equivalent. Okay. So that means from R1, by applying finitely many elementary row operations, we can arrive at R2 and vice versa. Okay. So elementary matrices are invertible, we have seen, right? Elementary matrices are invertible, and so is their product. So therefore we know that there exists an invertible matrix P such that P R1 equal to R2. So from here it follows that if some row, let us say if the jth row, the jth column of R1 is 0, then so is the jth column of R2. Why so? And then similarly vice versa. That is, if the jth column of R2 is 0, then jth column of R1 will be 0. Why so? That is very easy to see. So, if you remember how when we made multiply two matrices, what are the columns of this product? If the columns of B is the columns are B1, B2, Bn, then the columns of AB is AB1 up to ABn. Okay. So, thus the jth column of R2 will be P times the jth column of R1. So, if the jth column of R1 is 0, then when you multiply that by invertible matrix, or in fact for any matrix, then it will be 0. So, this is actually trivial. Okay. So, that shows, I mean, that helps us in the proof a lot. So, what we will do is, as I said, we will prove by contradiction. Since R1 not equal to R2, so there will be some column, let us say some j, such that the jth column of R1 is not equal to jth column of R2. So, at least that is they will disagree at some column. So, let us say this is R1 and this is R2. Remember, both are row echelon matrices. So, let J be the first non-zero column of R1, that is everything else left to that is 0. Similarly, before the jth column in R2, everything else will be 0, all the columns will be 0. Now, regarding the jth column in both R1 and R2, as I said, this is the first non-zero column. So, here it has to be 1 0 0 0, because the first non-zero column, okay, in the row echelon matrix. So, there are two possibilities. First of all, you might think that the jth column of R2 may be 0, but that possibility is ruled out, okay, because the jth column R1 is non-zero. So, therefore, this also has to be same 1 1 1 1. So, we see that the disagreement does not happen at the first non-zero row of both R1 and R2. Okay. So, that is there is one pivotal, at least one pivotal column, namely the first pivotal column, which I mean there is there is at least one pivotal column which is same to both the matrices. Now, what we do is, it's a nice trick, you can say that we choose the well, so before that let us write that let K be the first non-zero column where they differ. Okay. So, let us denote the non-zero column for R1 by Aj, and well, for let us make it much simple. So, let us call it some C for, so C is the jth column of R1 and similarly C prime the jth column of R2. So, C and C clearly as column vectors they are not equal. So, what we do is from R1 we will make the following matrix R1 dash in the way that the last column of the R1 dash will be this C, and before that we will pick up all the columns left to the kth column in R1 which contain pivots. So, I repeat, so C is the kth column of R1. So, we put the kth column as in the last column of R1 dash, and left to that we will pick up all the columns. So, let me first label somewhere. So, suppose this is K, the kth column where the disagreement happens. Okay, disagreement happens. So, we pick up the kth column and all the columns in R1 left to this containing pivots. So, therefore, the matrix will be like this. So, so in this matrix the last column is the kth column of R1, and the all other columns are just the columns containing the pivots in R1 arranged in the order in which they appear in R1. Similarly, that is what we can do for R2 as well. Let us denote that matrix as R2 dash. So, it is C dash, and as you see that before the jth column, this portion and this portion, sorry, is the kth column, this portion and that portion, they are identically equal. So, therefore, the columns which contain the pivots here left to the kth column in R2, these are the, those are the, yeah, again let me repeat. So, the columns which are left to the left kth column in R1 which contains the pivots are same as those in R2. Okay. So, therefore, here also this R2 dash matrix will look like this. Okay. Okay. So, how did we arrive at R1 dash from R1? Deletion, by deleting the columns in the left side of the kth column which do not contain pivots, and the columns starting from k plus 1th. Okay. So, basically this matrix here has been obtained from R1 by deleting some columns, and the same columns are deleted here. What does that show? Observe that deletion of columns do not affect row equivalence. So, this is the main observation. Deletion of columns do not affect row equivalence. So, what I mean by this is the following, that is, suppose I have two matrices which are row equivalent, and from the first matrix, let us say I deleted the columns J1, J2, Jr, and I delete the same columns from the second matrix. Now, after deleting those columns, the smaller matrices that we get, they will also be row equivalent, because it is very easy to see you are actually operating with the rows. So, on each row the operation is going on, I mean on the entries of each row. So, if you remove a column, then apart from that column, on the all other columns the operation is still being performed. Okay. So, and the formal argument you can give in terms of matrices, because if from B you remove some columns, then the other columns in AB, then the other columns in AB will be precisely the product of this A with the columns remaining in B. Okay. Fine. So, from this observation you can give a rigorous proof. So, I left that to you as an exercise, but it's now I think you will now agree to the fact that from your intuition says correctly that since you are operating rows, so on each column the elements the entries which are in the rows are being operated. So, if you delete one column, let us say, then the same the operation, the row operation that you are applying, elementary row operation, that is still happening on the other rows. So, if you just delete one column from here, one column from there, then the earlier operation which is bringing the this one to that. So, after deleting the columns, you see, since on the other row, on the other columns there is this row operation does not have any on the other columns, the same row operation, the same changes along the changes in the entries are happening, right. So, therefore, they are equivalent. Okay. So, now we are about to finish the proof. So, IR and IR, so the R1 and R dash, R2, R1 dash and R2 dash are row equivalent. R1 dash and R2 dash are row equivalent. And that will give us something very interesting. So, let us see that what can happen in this block, which is the bottom right block. What can happen here? Of course, these are completely 0. Okay. What can happen here? This is the first observation. Remember, both these are coming from row echelon matrices. Let us see. So, for R1 dash, we have two choices. Choice 1 is having a matrix of this form. Let me rather do it here. So, for R1 dash, there are two choices. So, the first choice is, so RA will be as usual. What happens here? So, one choice might be this, I am saying that, the other choice will be, so for R1 dash we have two choices, the other choice can be let us rather write them as let us say Z1 up to Zr, where Zi is there anything, I do not care. Why so? This is because if here, like in this block, try to understand, if there is anything non-zero here in this block, then suppose you take the first non-zero. So, I mean below this point you take the first non-zero element, if anything non-zero, any non-zero entry lies here. So, below this point, if you go from top to bottom, pick up the first non-zero entry, and you see that happens to be the first non-zero entry in its corresponding row, right, in R1 in fact. So, if let us say in ith here, in the ith position you have a non-zero entry, then before that everything is 0, right, because we have already considered all the columns which are containing the pivots. So, the row so this row has a non-zero entry, means this row has a pivot, and the columns which contain pivots which are left to the kth column are already considered. So, this means since a row echelon form, this has to be 1, that is this has to be 1. So, once this is the 1, then you see since this is a pivot, everything else will be 0, and this has to come at the right after. So, this pivot has to come right after, right after this identity block, that is at the r plus 1th row. This gives us this matrix. I repeat, if anything non-zero, any non-zero entry lies here, so that means in the kth row of the R1 you have a non-zero entry somewhere. So, this means the corresponding row has a pivot, okay, it has a pivot, and which column can contain the pivot? So, either this will be the column that contains the pivots, or any column which is left to that, but I have considered all the columns left to that which contains the pivots, and these are I1 of r minus 1, okay. So, that means since I have considered all of them, this has to be the pivot, therefore, this has to be at the r plus 1th row, this has to be the pivot of the r plus 1th row, that gives me this, otherwise it will be the below block will be entirely 0. So, these are the two choices for R1 dash. Similarly, for R2 dash there are two such choices. So, for R2, okay. Now, let us compare one by one. Since R1 dash and R2 dash, they are not same by our very construction. So, there will be two possibilities, either R1 dash is this and R2 dash is something of this form, or vice versa. Okay. So, we will prove one, and the same proof goes, we will settle one possibility, that that it is going to lead us to a contradiction. So, the same goes for the other possibility as well. So, therefore, assume that this is now the R1 dash and this is now the R2 dash. Okay. Now, that is a very good situation, because this is a matrix having at least 2 columns, because in the beginning we have observed that the disagreement cannot happen at the first non-zero column. In fact, the first non-zero column of both the matrices will be 1 0 0 0, because initially if R1 dash is 0 and R2 dash is non-zero, then if R1 is 0 and R2 is non-zero, then certainly R1 and R2 cannot be row equivalent. Okay. So, if we exclude the 0, if we have excluded the 0, that null, that's trivial possibility in the beginning, so we can assume both R1 dash and R2 dash are non-zero. Therefore, their first non-zero column has to be 1 on the top position and 0 elsewhere. So, is a system having at least one variable. Okay. So, what is the system corresponding to this R1 dash? Easily see if the variables you label by x1 up to xr. So, the x1 equals to 0 plus plus plus, xr equals to 0 and xr plus 1 will be 1. This is the system, and what is the system here corresponding to that? You see there x1 equals to z1, xr equals to zr and 0 elsewhere. Now, you see this, since these two matrices are row equivalent, so therefore, corresponding systems will have same equation, but this system does not have a solution, whereas this indeed has a solution. So, that shows that it is not possible that R1 dash will be of one of these two forms and R2 dash will be the other. Okay. That settles the proof of uniqueness. I repeat, the way we did, we choose the first non-zero, we choose the first column where the disagreement starts. Okay. So, let K be that column. So, we picked up the kth column and all the columns before that containing the pivotal elements. Okay. So, it is quite clear, right. So, that leads us to this matrix R1 dash and R2 dash. Now, the possibility is kth row, let us say in kth row in R1, either that contains a pivot or that does not contain a pivot. If that contains a pivot, then R1 dash will be of this form. If that does not contain a pivot, therefore, anything here has to be 0. Okay. Because if anything here is non-zero, then this let I and anything here means in the rows after if you have R such columns contains the pivots before the kth column, then the rows starting from R plus 1 to m, in the rows there will be a row which has a non-zero entry lying here, and that means this row has a pivot. Okay. So, that means either its pivot is contained in in one of the columns, pivotal columns left to the kth column or not. Okay. So, since I have considered all the columns before that, so therefore, if this contains a pivot, then this. So, since I have already considered all the columns before that, then therefore, we have only these two possibilities. Same for R2 dash, and we see that it cannot happen that R1 is one of the R1 dash and R2 dash of this form and other one is of the other form, other one is of the other form. Okay. So, I think with that I will finish this lecture. So, I have just given you the sketch of how the sketch in fact more or less the complete argument of the proof of uniqueness. The formal, so writing it formally in the typical textbook style, that is necessary, and as usual likewise to the proof of existence of row echelon form, I am leaving that to you. Okay, with that I will finish. Thank you.